Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, we'll be covering emission spectra, Rutherford's model, and Bohr's model. Let's get started. So as we learned in previous videos, atoms are able to interact with light and absorb the energy from that light. And when they do this, they actually can be promoted into additional or higher energy levels and then release some of that light as energy as they relax back down. Now, this is really the foundation between things that we see on a day-to-day basis, like neon lights or fireworks. Now, when that light that is emitted is passed through a prism, a pattern of particular wavelengths of light is seen that is unique to that type of atom or molecule. And this pattern is what we know as the emission spectrum. Now, it's important to note, unlike the white light spectrum that you would see, where you see that continuous rainbow or that Roy G. Biv spectrum, the emission spectrum is not considered to be continuous. And so there are discrete breaks in between the colors and subsequently the wavelengths associated with that energy that's being given off. Now, we can use this pattern that we're going to get, this fingerprint almost, to identify the materials. And this is also associated with some flame tests that you may do in the laboratory. And so what happens, if you see here, we have these gas tubes or even neon lights. As the molecules in there are able to absorb some energy, when they relax back down, they emit energy in the form of light, and you end up seeing these distinct colors associated with those materials. Now, one of the models that we often follow when we think about the structure or the shape of an atom is Rutherford's model. And in this model, we found that the atom contains a very tiny, dense center called the nucleus. Now, the nucleus, remember, that contains our protons and neutrons. It has the majority of the mass of the atom. But despite that, it only makes up about 1/10 of a trillionth of the volume of an atom. So it's very, very small compared to the overall size of the atom. Now, although it's that small, again, the entire mass of the atom is found there. Remember, the mass is found based off of the amount of protons and the neutrons that are found in that atom. We know that the nucleus is positively charged because of those protons that are present. And then the remaining size that is attributed to that atom is based off of the electrons that are there. And oftentimes when people think of an atom, you kind of think of that well-known picture where you see those electrons that are orbiting, traveling around in that empty space. But what we're going to learn in these subsequent slides is that, in fact, they're not moving in that manner, but are actually located in a different manner. So there are some problems with Rutherford's model. And one of those big problems is the fact that electrons are charged particles. And so if they were moving the way that we constantly see them depicted, well, then there would be all this energy being given off from the atom. And since that energy is just constantly given off, you would expect that any atom should glow. And after a while, there would be, and because there's no source coming in, no energy being input, eventually the electrons should lose all the energy associated with them, and this should cause the atom to collapse. However, we don't see this process take place. So there has to be some other definition or some other explanation for how and where these electrons are situated and what's feasible. So one of the models that we look at to understand the atom is the Bohr model. And so the nuclear model of an atom does not explain what structural changes occur when the atom gains or loses energy. So Bohr actually developed a model of the atom to explain how the structure of the atom changes when it undergoes transitions. And so his major idea was that the energy of the atom is quantized. And quantized just means that there's a specific amount of energy in the atom related to the electrons' positions in the atom. And so quantized means that the atom can only have a very specific amount of energy. And again, we're not having that constant evolution or release of energy because those electrons are moving around in circles. So what we do see is that the electrons can travel in orbits that are fixed at a fixed distance from the nucleus, and these are called stationary states. So therefore, the energy of the electron is proportional to the distance of the orbit from the nucleus. Now, in order to transfer from one energy state to another, electrons have to absorb energy from someplace. And then as they go down from higher to lower energies, they would be emitting energy in the form of some light. Now, that light that's being emitted is that photon of light that we talked about in previous videos, and the wavelength associated will be dictated based on how far of a transition they're undergoing. And so just shown for you here is a model of an atom and the related emission spectra that you would expect from the transition from some of these different stationary states. And so you can see when you're transitioning from like the third energy level to the second, you get a red wavelength, a much longer wavelength, so less energy. But when you're going from like the fourth energy level to the second, well, now we have shorter wavelengths, higher energy. Or from the fifth to the second, we have an even shorter wavelength, even higher energy. So the more energy is associated with that transition from higher to lower energy levels. I hope this video helped you understand spectra, Rutherford's model, as well as Bohr's model. Be sure to like, comment, and subscribe, and let me know what other videos you would like to see in the future. Have a great day. Talk to you guys later. Bye-bye.